Okay, Bismillahirrahmanirrahim. During the last class, we have started the filter design from analog circuit point of view. We'll try to finish this part quickly and move to the digital segment. We'll follow this chapter number 8 and 9 for understanding the analog part, which will give us the fundamental base to understand the filter from the digital point of view. Okay, so if we continue the fact, we have talked about the low pass filter in the last class, as well as the high pass filter. So the two kinds of the filter. So basic things we have already studied. So if we look at the band pass filter as well, so this is the circuit. I will not discuss the things line by line, equation to equation. You can please go through these things. It will basically give you the strength to understand and explain the facts properly. So based on the previous experience, we can develop the equation, final equation like this in the S domain. And as we have already mentioned that by plotting the magnitude response, we can understand the filter, the order of the filter. For the band reject filter as well, okay, first of all, we need to design the filter and then we can analyze the filter as well. Very important fact, this is very general facts. Of course, we need to understand the things very deeply. Why we are not encouraged to use the passive filters? What are the passive components? We know that the resistor, inductor, and the capacitors are the passive elements. And with the contrast of this, the transistor is one of the examples of the active elements. If we tell the fact, what about the diode? What about the diode? Whether this is active element or a passive element. Do you want to answer that? The diode is an active or passive element? Any of you? Okay. So what is the characteristics of the active element? In case of active element, you can say this is a transistor. You can power up the things, and you can have the ability to amplify or de-amplify the signal. You can control the amplification of the signal by the active element. This is one of the characteristics, but there are some other characteristics as well. So from that point of view, diode is not an active element, because what you can do, you can just take some part of that and you can block some part of that. But there is no point to use the diode to amplify or de-amplify the signal. Okay, that's why this is not an active element. This is of course, a passive element. And if we talk about the active element, like the transistor, the operational amplifier, the op-amp, is also an active element, because inside the operational amplifier, we have a lot of resistors, inductors, and transistor as well. And we also have one capacitor inside the transistor. Not only one capacitor, like there might be a multiple number of capacitors. So that's why the transistor is known as an active element. So why we shouldn't use the passive element or the passive filters for filtering? I believe that you have these ideas. Just to recall the things, whenever we are cascading the several stages of first order filters produces the loading effect on circuit, and this result in the output and getting drastically reduces. So you know that this term is very important, the loading effect. So whenever we are introducing this kind of filter, as this is a passive element, it will also need the energy from the circuit. As I already mentioned that in case of transistor, we can give the power of this circuit. This is the signal in, so signal in, and this is the point where we are giving the power, the voltage in. So V in gives the energy to this circuit, by which you can control the output of the signal. S out can be controlled. On the other hand, in case of inductor, combination of inductor and the resistor, something like this, in this case, the energy basically come from both from the input side V in, which is the signal in as well. So the total circuit basically powered by the input signal. So it consumed the signals and it actually dropped the signal as a whole. So that is why this is not permittable or not a good idea to use the passive element. To increase the output, external amplifiers have to be incorporated in the filter circuit. So if you want to protect this fact we have discussed previously, then we need to add another circuit, the amplifier circuit, and as you can understand that will also consume the energy. So that's why this is not a good idea. Impedance matching becomes a big problem with passive filters. If I ask you what is impedance matching, definitely you understand that to transfer maximum power, you need to match the impedance of your input circuit to the output circuit, and that actually been a huge problem for the passive element. Why that is so? Why the impedance matching? In which case this impedance matching become a huge problem for the passive filter? Could you give me one example for which the impedance matching become a big problem for the passive filter? Can you give one example? Okay, let's think that this is your circuit, input circuit, and from where you are getting the signal, and after that you are putting the filter. So you're putting the filter, and inside the filter, what sort of component you have? You have the inductor, you have the capacitor, something like that. So whenever the signal frequency is changing, so signal frequency is going high or going low, depending on that, definitely the impedance of this total circuit, the parameter impedance will changes, and that makes a different situation. So that means what is the input impedance at this point? Z in, the value of the Z in is proportional or inversely proportional to the F. So proportional to F, or Z in could be inversely proportional to the F of this total circuit based on the design. So it means that whenever the frequency has been when the frequency will change, then of course the impedance parameters will be changes, and that makes a huge problem for the circuit. If the inductors are used in the filters, they are bound to produce noise of their own. So they are very simple things are there, but you need to understand the things very conveniently, because why we need to move from the passive element to the active element. This is a very key issue, and those are the points we need to keep always in our mind. Hence, it is quite common nowadays to use the active filters, which employ the op-amps as the active elements. Active filters remove most of the uh, difficulties what we have faced by the passive filters. Okay. Now we can move to the active elements and for the analog filter, and that is the first step to move to the actual analog filter design. We nowadays we never use the passive element for designing the filter. However, to build up the theoretical aspect, the passive filter design is very much necessary. Uh, in the previous section, we have learned about this process. Let's start with an example. Design a low pass filter. So you can move move through these, skim through these examples. Design a low pass filter for a cutoff frequency 1 kilohertz. So nothing to mention here. So we already know for the first order filter, the cutoff frequency is this from the previous sections. And we know that omega c is equals to, this is omega c is equals to twice pi fc. Fc is for the cutoff frequency, and from there fc is equals to this, where we know that fc is equals to 1 kilohertz. From there you can choose the value of r and c. Always we choose the value of c because it is not available always in the market. So that's why what is already available, you can put the value, and based on that you can find the value of the r. If we have the fractional value or any value of r, we can tune it by the potentiometer. And this is the first example of that filter. Okay. For the second order filter, as we already know that if we do it with the second order filter with the same cutoff frequency as mentioned earlier, 1 kilohertz, then this is the formula we have already developed, and we know that. And from there we have two components like L and C. As we already mentioned that the C, you can choose any value of C which is available in the market, and after that you can choose the value of H. However, we need to think about the value of L as well. Very high value of L will produce some noises and the heat as well. So that's why we can choose our value of the C in such a way so that it is not more than 1 Henry. So it should be less than 1 Henry if it is possible. So we can control those values as well. And this is for the higher order filter. For the higher order filter, what we can do, of course, we can make the cascading of the two filters. For example, if we have the transfer function mentioned as Hs is equals to omega c over s plus omega c for the first order, and for the second order this is omega c square over s square plus twice lambda omega c s plus omega c square. So here omega c is the cutoff frequency. This is the actual frequency in normalized frequency. For introducing the third order filter, what we can do, we can make the cascading of this one. The cascading means we can make a multiplications of these two filters, which will cascade the things. On the other hand, so the things are pretty simple. You need to cascade. That means you can multiply this with the Hs for the second order filter, s square plus twice lambda omega cs plus omega c square, something like that. And you can find the third order filter. For the second order filter, just to understand the things, we can write this equation as well, because we have a target to find out the poles and the zero location from the fundamental equation like this. From there, we are basically targeting the cutoff frequency. We are targeting the cutoff frequency point. However, we need to know about the pole and zero locations in the z plane, and from that point of view, we can write this equation as this one, from where we can say that, okay, the denominators are equal, and from there we can write this sort of equations where we can mention that this is our pole locations of the system. These are the pole locations of our system, and of course for this example those are the complex pole, and we can derive it very easily that the omega c square can be mentioned by this. If we know the value of A and B, then we can of course relate those value to the cutoff frequency, as well as whenever you know the cutoff frequency and the value of A, you can also find the damping factor by this equation number 11. And it has mentioned here in this book that this is very important fact, that equation number 8, 10, and 11. So 8, 10, and 11 are the basic equations that are used in the design of the second order filters in analog and the digital signal processing. So you can go from the analog to the digital with these functionalities, because in case of analog filter design, of course the things are based on the cutoff frequency, and also in the discrete domain we need the cutoff frequency, as well as we need to plot in the z plane. In case of S domain, we need to plot it in the S plane, as we have mentioned earlier. But these are the things, that means we can design the filters in the analog domain like this, and we can move to the pole zero locations like this. And as we can understand that the S plane can be converted to the Z plane very easily. So if you can plot it in the S plane somewhere else, okay, those are the pole locations, it is very convenient to plot it in the Z plane as well. Okay, so we know that how to do that. That means we can convert it from the S plane to the Z plane. And that's why these are the core equations for designing the analog filter, as well as to the digital filters or digital signal processing. Filters using the operational amplifier. So far we have discussed everything based on the passive element, and we have learned how to build the filter both for the first order and second order, and we can make the combination of those. Now if we follow this equation, the previous equation, we know it that this is the equation. If you can recall that, okay, this is for the first order filter, where we know if omega c is equals to 1, then what we can write, hs is equals to 1 divided s plus omega c. Oh, okay, sorry. We can say 1 plus s. Okay, so why we are taking omega c is equals to 1? Just to make it simple. And afterwards, whenever you have done all the calculation, then you can put back your omega with any other value. So whatever the value of the omega c, you can replace it, and you can complete your calculation. So that's why there is no problem or any harm to take omega c is equals to 1. You can say this is again a normalization of the cutoff frequency. Okay, so let's start with that. So for the first order filter, we know that we have already, so try to understand that from the scratch, we have developed this equation, omega c divided by s plus omega c. From there, omega c is equals to 1, and from there we have this. So we know each and every part of this equation. And from that equation, we can also develop this. So very simple, but very important for understanding. We are talking about the first order filter. And now from this equation, we can write it very easily. And from this, by doing the inverse Laplace transform, we can do that. And how we have done this? Yes, definitely. This is very simple. Ys in s into ys, so is equals to minus ys plus xs. So of course, this is very simple task to do. S into ys, if you do the inverse Laplace transform, so we'll get dyt divided by dt is equals to this one minus yt plus xt. Okay. So we have found this equation in the time domain. Now we are in the time domain. Now how we can show this equation number 8.22 in the block diagram. So this is the block diagram, where you can understand that minus yt plus xt, adding two parts, so this is minus yt and xt, will produce these things. So that means after whenever that will summarized, that will produce these things. Now if that will be that will given or passing through a integrator circuit, what it will produce? It will produce definitely when it will passing through a if that is passing through a integrator, summing integrators, summing an integrator, then what it will give? So integrator gives yt, and there will be a negative value, so it will give a minus yt. So this is very logical. Don't think that where is the signal, input signal. So you are giving the xt, and the feedback came from here minus yt. They are adding together, so summing. So who is doing the summing? There is a circuit summing, and afterwards they are integrating the things, and this is the output. We got the output, and then we are giving the inverting the fact, and again we are getting the final output. So by having minus yt and minus xt and minus yt, we are getting the final output. And this is the whole aspect of this diagram, this diagram to the equation. Sorry. Okay. Now there could be some question of this aspect. How we can find this signal? There is no input signal of this kind of architecture. It may appear that here you can see this block. It may appear that we are generating the desired functions from nothing. Why that is so? Because as you can understand that we have got the yt, but how we got this yt, how this yt is has been generated. What is xt? Xt is your input signal. What kind of relation between xt and yt? Yt is the filtered version of the xt. So it is always the fact that in case of the signals or the systems of the analog circuits, we can produce the noise inside the signals. We have thermal noise, and the range of the thermal noise is from 0 to 10 to the power 13 hertz. So that is a huge range of the signal. And basically what we are doing, we are designing our filter accordance with our input signal in such a way so that we can get our desired output signal. So that means we have the input signal and we have the noise signal, which gives the feedback of the circuit. So if you can think of what is the value of minus yt at the beginning, that is a question. So it is the range from 0 to 10 to the power 13 hertz. So any value. So we are taking the range of the frequency to the input as a feedback, and the time to time it gives the value to that. And what we are doing, we are building a filter. It could be a low pass filter, high pass, band pass filter targeting a particular omega c. In our case, that is equals to 1, so that we can get our targeting frequency to the output. So that means we have a range of signal, and it can be noted as a DC to infinite frequency, because this is a very high frequency, 10 to the power 30. And for that, we can design our filter. As you know that the integrated circuit, the summing integrator circuit also can work as a filter. So this concept is very important to understand the IIR and FIR filter. So in case of analog filter, as we have already mentioned, that this is the core part of the analog filter. This is the first order analog filter. We are talking about this. In case of first order analog filter, this is the presentation of the filter, and this is a must component of the block diagram, where we need two operational amplifier. One is this and another one this. This one is just to invert the signal to shifting the phase, but this one is used both for the summing and integrating this signal, which actually works like a filter in this case. And we have learned that we definitely need this feedback circuit for this kind of orientation. So that shows that for any kind of filter presented by the analog circuit, always need the feedback. Without any feedback, you can't imagine any analog filter practical representation. And that is why all of these are having the feedback, and that's why they are a kind of IIR type. So there is no FIR type, finite element type filter. So we all have the infinite duration impulse response filter, all the analog circuits. Okay, and that those things I have already discussed are also presented here. So please go through this literature. Now we can develop a setup to solve the differential equation with the similar fashion. So if the equation is like this, okay, as you know that all the filters can be represented, all the circuits can be represented with the differential equation. So if this is the differential equation, then we can present it like this. Okay, so please go through one by one and you can present. So by this equation number 2 can be presented with this block diagram, with the representation of the having the reference of the previous structure. Okay, so to find this third order segment, so of course this is a third order filter, we need this segment, this segment, this segment, and this segment. So we have 4 inputs. So these are the 4 inputs. So this is the input number 1, this is input number 2, this is 3, and this is 4. Please go through this diagram, and I believe that you found it very simple for understanding. So this I represent the integrator circuit. These I's are the integrator circuits. After doing the integration, we got this output. So if we take this one, after integration, we got this result. That means what is the input? Of course, the input is this one, because the integrator does the integration as well as changing the symbol as well. So integrating and making the symbol output. Okay, changing the output of the symbol. So they are explaining this whole circuit. So please go through this. Nothing very very difficult. Okay, and now if we closely look at to this part, what we can understand, we have 1, 2, and 3 feedbacks and 1 input to the integrator circuit. And of course, this is a summing integrator circuit because they are summed themselves and integrated as well. So we know that a summing integrator circuit from our basic understanding, and the circuit looks like this. So we can understand it by this one. This point basically from the feedback, this is came from the feedback, and this also came from the feedback. And only this one is works like the input signal. How the feedbacks actually been generated, I have already mentioned that you have a huge range of the signal from 0 to 10 to the power 13 hertz. From there, any part of that signal will be filtered, and then it come back to the input side, and there you need a bunch of feedback signals, cycles of that signal to stabilize the output. Okay, forget about the core content. Now we are talking about this part of this of the segment. We can understand this by using this very simple summing integrator circuit. We can replace this. We can present this core part of this differential equation solving block diagram. And of course, by doing the integration, we got this output minus V0, and from each and every part of these branches, we can also find the proper value of the R to execute this number. That means what would be the amplification gain of each and every channels. So for the last one, the amplification gain was 1, and for the second last, it is 5/4, and from the first one, this is 3/8 is the amplification gain. So to do that, we can choose the proper value of the R to find out the amplification gain. They are in the mega ohm range. We can put it in the mega ohm range, no problem with that. But we need to think of the range of the value of the R in such a way that their performance should not go beyond the range of the values. So we can, what we have understood by this segment, that whenever there is a filter, any sort of filter can be presented by a differential equation. For the first order filter, we have started with 1 plus s. Definitely we can design our second order filter like that. Definitely in case of second order filter, we have d square yt by dt square terms will be there, and from there we can design our analog filter by using the operational amplifier. So this is the fact we have already covered. Step number 1, you need to design the filter in the analog domain. Whether this is an active filter or passive filter, we don't care about this. That's just from the active element, sorry, the passive element, the inductor, the capacitor, by the resistor. By using this, just by understanding the fact, you can design your filter H omega. From there, you can design this HS. You can move to the inverse Laplace transform. You can come to the time domain, and from the time domain, you can draw your block diagram, and that is all. So you can design your passive, you can design your active filter. This is the active filter. So you start with the passive just to understand the fact, but you can design, you can replace your passive filter to the active filter, and which is the core part of the filtering in the active domain. There is a different way to, there is another way to represent this analog architecture. We have shown it earlier by this kind of integrator, summing integrator, and by using the integrator. So those are the two elements we have used. Definitely there, whenever there is a feedback, you might need the amplification part as well. Now the same equation or the same differential equation can be presented by this kind of block diagram. Okay, the same equation we are presenting here. Now this is the summer circuit. Of course, we know what is the summer circuit. This is the multiplier. This is also the multiplier. This is multiplier. And this is the integrator or the delay unit. Integrator or the delay unit. I'm just putting this question to you. Why the integrator is considered as a delay unit? This is the question. Why the integrator circuit is considered as the delay unit? Okay. In this book, it has been mentioned that it is well known that the integrator circuit is known as the delay unit. But I have found that many of us do not know why the integrator circuit known as the delay unit. We need to prove that. So if you go to the circuit analysis of the integrator circuit, a simple first order integrator circuit, then what we have found that all the signals can be delayed, and it is based on the capacitor. It is based on the feedback capacitor. So if this is the transistor, okay, we have the input signals given to that. I'm talking about the summing integrator. You can talk about only the integrator circuit as well. So in that case, we have found that the delay actually been controlled by this capacitor. So in case of analog signal, you can choose a value of the C in such a way that you can control the delay with the time value. In the digital domain, or the discrete domain, not in the digital domain, in the discrete domain, you can control this integrator part. We do not need to design it with the circuit like the operational amplifier, but we can use it by the flip-flop. We can use the flip-flop to control this delay value as well. Probably you can understand. So how to introduce the delay? So here the delay means the physical delay in the circuit. Physical delay. So the time delay is equivalent to the integrator circuit in case of analog. In case of discrete signals, this integrator or the delay can be represented by the flip-flop. Flip-flop. You can use different sort of flip-flop to make this delay as well. They are equivalent to the delay circuits. So from your previous experience, I believe that you can explain this architecture of following differential equation, how to find the output. So the feedback, always this concept is very important. So how you understand the concept of the feedback, why this is important to to know about the feedback in case of analog circuit. Always to present any sort of filter, whether this is first order, second order, or any sort of order of the filter, we need the feedback. And that is why FIR type filter is not possible for the analog case. Okay. So as I have already mentioned, that D flip-flop can be presented, can be replaced by this delay circuit. Okay, so that is the end of this chapter. What was the focus? What was the focus of this chapter? Number one, to understand the analog filter from the scratch, design the analog filter. From the analog filter of the passive element, how you can move to the active element, and that is the building block of designing the digital filter in the next chapter. In the next chapter, means in the chapter number 9, we'll start it. We'll talk about the step-by-step procedure for the design of the analog filter using the Butterworth and the Chebyshev approximation, the most popular two filters in the filter domain. And the later we use this procedure for the design of the digital filters of the Butterworth and the Chebyshev filter. It is in the chapter number 12. So if you have any question at this moment on this chapter, we can discuss on that. Otherwise, we can move to the chapter number 9. If you have any question at this moment, okay, let's start chapter number 9. That is, the chapter name is step-by-step design of analog filters. Particularly, this actually focusing on the Butterworth approximation and the Chebyshev approximation. So currently we use 4 types of mathematical function to achieve the required approximation in the response characteristics of filter. These functions, which are used for the design of filters of the recursive type. Recursive means we need the feedback, are the Butterworth approximation, Chebyshev approximation, elliptical approximation, and Bessel's approximation. Why the names are like approximation function? First of all, we need to know the process. First, people try to design the filter by mimicking it with an approximation. Let's say we have we want this kind of filter. We want this kind of filter, low pass filter. However, it is not a very much convenient to design this kind of filter due to various facts. Then people try to understand, okay, what are the problems? Then according to the Butterworth filter, they have designed like this, okay? Let's say design like this. From the Chebyshev approximation, they have designed the fact like, okay, the filter might be like this. There are some ripples in the pass band like this, and the flat like that. And in the Chebyshev domain, there might be some other kind of filters. There might have the flat region in the pass band, but in the stop band there are some ripples. Okay, so there are some approximations. By mathematically, they have first designed the things, and afterwards they want to implement that in the circuit. So first it comes in the approximation by putting the hypothesis in the magnitude response, and afterwards it actually followed by the circuit with their design. Okay, we have the circuits, we try to follow the approximation with the actual circuit. So which one actually came first? First, the approximation. That means approximation function, the mathematical tools. We want to design our filter with some approximation. of the magnitude response. We target some magnitude response. We try to design it with the circuit. Definitely there are some trade-offs. There is a theoretical part and there are some practical part. Okay, let's start with Butterworth approximation step by step. How to build that approximation as well. Okay, so this is very important to understand, and I have found very easy from this book as well. Okay, so let's start with the very scratch. So we know this. You can do that H omega. So from any circuit you can build it. We have built it from the first order filter. Very simple RC circuit. You can this is C, this is R. Very simple RC circuit. You can design this low pass filter. Now about the squared magnitude of the filter, we can also build it from this equation. So very simple. Now from there, what we can do, okay, we can do the square root of each part and we can find this equation. Very simple. Now this is for the first order filter. Now if that is for the nth order filter, what will happen? So this is a mathematical terms. You can do it. And this is the polynomials of the nth order polynomial order, nth order polynomial equation. So I can utter this one. The equation 9.4 represents the Butterworth polynomial of order n. We can design analog and the digital filters based on this approximation function. So this is the bottom line, or sorry, this is the starting part of designing the analog or the digital filter by the same approximation. So this is the approximation. So this is the mathematical approximation for the Butterworth filter. Now for different, let's say, in many cases, H omega is expressed in decibel. So if we want to express in decibel, then we can put 20 log H omega, and then we have found this equation. This is exactly the same what we have found earlier. So the same equation. This is these are the same. Equation number 9.4 and 9.5 are the same. And in case of Butterworth filter, this is known as maximally flat response, because we are not having the ripples in the pass band, the character response, pass band response of the filter. We'll see that. This is the characteristics of the Butterworth filter. So almost it is a flat one, though in theoretically this is not flat like this. And of course you can design the first order, second order, and third order filter. So by changing the value of the n is equals to 1, 2, or 3, it will show different order of the filter. And this is the equation we have already built before. Okay, so this is the first step to know the approximation. Now we can introduce the Butterworth filter, the design of the Butterworth filter. What are the key parameters we need to know to design the Butterworth filter? We need this passband gain, which can be represented H1, which is given as 0.9. In normal value, it can be given as the decibel value. Okay, first of all, the normal normalized value is 0.9. What is the maximum gain? Of course, the maximum gain is 1 for all the filters. So the passband gain is 0.9 and the frequency is omega 1. What is the stop band gain? This is the stop band gain 0.4, and what is the stop band frequency is omega 2. What about the cutoff frequency? The cutoff frequency will not be given for the Butterworth filter. It will be calculated automatically by using the order of the filter. If we have different order of the filter, for different order of the filter, we have a different cutoff frequency. Okay, so for For starting the design of the Butterworth filter, we need four things: H1 omega, H2 omega, the omega 1, and omega 2. This H1 belongs to H1 omega and H2 belongs to this one. For this case, it has been given, this is 0.9 and this is 0.4, and practically this should be given. Let's say this is 1 kilohertz, and this is 10 kilohertz for the low pass Butterworth filter. If we have these values, from there we can find the value of omega C. If we can find the omega C value, that is the design of the filter, and from there we can also design our analog circuit as well. Okay, always our target is to find the HS. From there you can find the pole zero locations as well of the filter. Okay, so it has been discussed here. What are the parameters we need? We need these four parameters to start the design of the filter. Design procedure for the Butterworth filter. They have given the examples. First of all, the core architecture, the general structure, and after that, they are explaining the things with the examples. So first step number one is determinations of order and the omega C. Order of n and the omega C. We have this equation. We have learned that equation already. So there are two unknowns here. For example, small n and omega C. We know that we should know the value of omega 1, and from there we can get this equation, and we should know the value of omega 2. From there we should know this equation. So we have two unknowns and two equations. So these are equation number 1 and equation number 2. And what are the unknowns? Unknowns are omega C and n. So from there we can solve this. We can solve this and we can find the value of we can solve the values for n and omega C. Which one will come first? N or omega C? Cutoff frequency or omega C? What we can do, definitely the omega C can be any value. Omega C could be any value, but n should be a particular number, and it should be a integer number. If we got, this is let's say for any value of omega C, we got the value is 3.3. then what we can do, this should be converted as 4, because whenever you are improving the order of the filter, that is enough to catch your particular omega C, what you take to count the value of n. Let's say we took the omega C, omega C is equals to 8 kilohertz. For that one, we got the n is equals to 3.3. It should be counted as 4. Then what we can expect that even the cutoff frequency can be taken more accurately than the 8 kilohertz. That means you must stick on the cutoff frequency. However, if we can move to the 3, the n is equals to 3, in that case, it will give a challenge to the omega C, and maybe the omega C is extend to 8.1 kilohertz. So we'll see that example in the next step, of course. So up to now, we have found that how to build the architecture for the Butterworth approximation. In the next step, we'll see step by step design procedure for the filter. The next step is determination of the poles of the HS. So how to determine the poles of the filters. So we'll see that in the next class, inshallah. Okay. So okay, so we can stop it for today. So see you on the next class, inshallah. Thank you for joining.